So when we have this, I'll put them on. Did I give you the website on at COD? What the website is where it'll be there on the syllabus? I don't recall, but I will.
No.
I can add that up to you. Basically, let's start with this. By the way, I've got 2 TVs now, so here's our Hurricane. I guess it got upgraded. Still a little bit of circulation over here. That's cyclonic all in the outer bands, but if you look over here, you can see some of the anticyclonic circulation starting at least.
Marco and Polo?
Huh?
Marco and Polo?
Marco and Polo. Yeah, by the way, that first Marco was the lamest. That was a nothing. So people like, oh, there's never been 2 hurricanes in the Gulf at the same time. And the answer is, yeah, it still hasn't been. Because that became horrible. So let me go to this instead. I'm going to see if I can. I'm going to do this, I think. And I can put you guys all up on my second screen. So if you see me looking over the side, is I can at least kind of monitor what you're doing on over there. First of all, let's do logistics. How's the sound and everything? Good?
Yeah, I can hear things perfectly.
Okay, so that's good. So we'll go to the syllabus just to kind of talk through what we're going to be doing. As far as I'm concerned, guys, you're going to do the work. You're going to take some tests. And I'm hopefully going to give all A's and B's and C's. I mean, maybe a C if you're not doing really well. But basically, I want this course to reflect how much you learn. So I'm not going to worry too much about grades on this point. And I know most of you, I know all of you, so it'll be fine. So there's what we're going to be talking about, office hours, blah, blah, blah. Just so you know, our experimental text page is there. By the way, I've got to show you this. What do I want to do? I want to go here. Weather.satrad experimental. We're going to be doing a new experimental, or we're getting rid of our radar page that's going to be Flash. And right now, we're hopefully this week, this will go over. But if you ever go to this URL, for now at least, /exper, you can set it up as a web app on your phone and give it a try and play with that. So let me show you what it's going to look like. Here's the web app. I don't know if you can see, we got some bright lights. And are you guys familiar with making it as a home screen? When you go to a web page on your phone, you know where you can like share or copy the way that you look at that at the bottom of the page? There's something that says save to home screen, and it'll work as an app, and it's set up to be really good for your phone. You can do the 200 image loops. You have access to all of our weather products. You can pan and zoom on your cell phone, which is something we've not been able to do until now. You can save images. You can save loops. You can share page. You can look at active warnings. You can have, here's your radar selection, where you can say, well, this is actually kind of doing this now. So this is still, right now, the desktop is still being developed, but it's really cool. And so if you have a chance to do that on the phone, that might be a really quick go-to app. I know Radar Scope is better in some ways, but the fact that you can do a 200 image loop on this thing is pretty amazing. In fact, did you know there was a severe thunderstorm warning in northern DuPage County last night?
Yes, about almost 4 a.m. when I woke up.
I couldn't believe I saw that on my mail this morning. I'm like, whoa. So this is what happened last night. Some storms came out of Wisconsin, and they actually stayed together into Illinois. And then another one came through later, and this one was actually able to make it through northern Cook County and into Chicago. So anyway, I just wanted you to see that. So that was wow. So here's what it is. All assignments are going to be turned in on doc or PDF files. 70% on for your exams. So your homework and final project, And when I say final project, we're talking about a set of notes, which we'll go through in a little bit. So the most of your grades are going to be the tests. And I probably will give you take your test at home as much time as you need. Here's your course objectives. And there's a lot of them, but you can see what we're going to do. And pretty much we're going to do all of these. Advising, how it's going to work. It's just a virtual class. Because I know you all and you're willing to talk, I'm not going to worry about that. And James, as soon as you get a camera, I need you to get that.
All right.
Obviously, you got this Zoom meeting, which you know about, and that's where we'll be. God, so yesterday, I'm doing severe weather. I get up, Zoom is down. I couldn't even have class. And then my mic and my camera didn't work, and I have no idea why that was. It was a brutal start to the semester. Here's our topics, and that's it. Okay, so the first thing we want to go to is the class notes. Now in here, I think there's part of it that we want to talk about in terms of like the Greek alphabet. I don't know if you want to print that out or something like this, but you should know our letters. So we've, like in this class, we will have alpha. I think you probably know this lowercase alpha. We never use uppercase alpha for the similarities to Roman numerals. Then you got beta, then you got gamma, which we've used capital gamma, and we also have little gamma, which is just this little guy here. Now delta, we are going to use both deltas in this class. So capital delta, you know, small delta looks like this. Now epsilon is interesting because big epsilon is E, small epsilon is this guy, which we sometimes use, but sometimes we use this a little bit more curly. So keep that in mind. We have zeta, which we don't obviously use Z, but we use this funky guy. Anybody know what zeta stands for in meteorology? It's vorticity. It's a couple of other things, and it's one of the more confusing of the letters. We don't use H, obviously, for eta, but we use this little eta. I don't use capital theta, but we use small theta, although sometimes I will use capital theta because it's easier for my Epic pen to do. Iota, we don't deal with. Kappa, capital K and small k, but it's just pretty much a little bit curlier that we do, so we're going to use kappa. Lambda, we obviously use lambda for radiation and wavelength. We don't use kappa lambda in this class. Mu, we don't, that's a coefficient of friction. We don't use that in this class, I don't think at all. Now nu, and I'm going to do this, let me go to Epic Pen.
Our favorite pen.
Your favorite pen, and it should be because it's kind of cool. And typically what I do for, where were we? For new is it's going to look like that. So if you see that, so we have mu, and we have nu, which is just usually like a V with the curly. We don't use it very often at all. Then this one, psi, this is another type of vorticity. So we have relative and absolute vorticity. That's a pain in the butt to try to draw that guy. So it's actually takes some practice. And nobody ever wants to draw that one, and I don't care. Pi we use, obviously. Rho, obviously. Oops, let me do this. Sigma, capital sigma we know, and small sigma. I've never seen this guy here, but this guy sigma, super important. Little sigma. Tau is usually used for what we call torque, or no, there's another one. It's a dyadic or something. It's like a shear vector. Upsilon, I don't see us using that very often. And here's the big one, phi. We will use capital phi. We use small phi, and they sometimes make it as like a cursive one, but I always do it this little guy. and it's going to be phi or phi, 2 omega v sine phi. Phi is what we usually do. I know some people in like sororities use phi. Chi, I don't know if we use that. Psi is a stream function. And then omega, we're going to use both capital omega and little omega. So let me ask you guys this. Do you know what those things stand for?
I know little is
Fast.
wavelength, right?
No, wavelength is lambda.
Oh, it is lambda.
But omega, big omega
Phase.
is the Earth's rotational frequency.
Oh, okay.
We use 2 omega v sine phi for the Coriolis force. We're talking about the Earth's rotational frequency. But anytime something rotates, we're going to use little omega. So capital omega is simply the Earth's rotation. Little omega is any other rotation that we're talking about. So that's just something that you might want to know about. So it might be a good idea that you print this out. I don't know if you're going to keep a notebook or you're going to do it on your computer. I guess you have the chance to do whatever you want. We've got some worksheets that we're going to be working on, kinetic theory. Second worksheet, there's some Carnot engine reading. We really don't have a worksheet to go with Unit 3 because by the time we get to Unit 3, you should have established a pretty good working understanding of what we're doing, and then it's just pure lecture note-taking like before. In here, have you guys ever heard of or seen the mechanical universe?
I don't think so.
Oh my God, love this. So I have some stuff on here from the Mechanical Universe. This was one of my favorite TV shows. I love this guy. It's simplistic. I think it's at about a lower college level. He gives obviously high-level college lectures, but they kind of simplify it. But they do talk a little bit about derivatives. He's got a lot of information that is just awesome. And so we're going to do a bunch of these in class. I've got a couple of other even worse videos. We will actually show 2 nightmare videos. Students who have taken this class know it's a nightmare. They're in black and white from the late 1960s. They are done with extraordinarily primitive computer. I'm telling you, I wish somebody could do it up to date because it's phenomenal. And I've never seen anything that could come close to these things. One of them is called Waves and Fluids, and the other one is called the Eulerian and Lagrangian description of fluid mechanics. And we will go through it and rip it apart and pull it apart and talk about each thing in there. It's as good a video as ever has been, and it just takes us some time to really unpack it. So there's your information. I want to take a look at Unit 1 worksheet first of all. Oh shoot, I hate when it does that. My computer has a security program which I have to go in here and say, unblock it, because it's from another computer. So I can never open it up directly. Okay, so in here, this is what we got. I got to do 2 things here. Do you have your book?
Yes.
Mm-hmm.
So here is the book. Is there any of you that don't have this yet?
Still waiting
Okay.
on it from the bookstore.
What?
I'm still waiting on it from the bookstore.
When are they going to get it?
I don't know.
I thought they had 1-day turnaround.
No.
Ooh.
God.
They have it at Amazon.
Well, if you ordered it, it'll be there soon, hopefully.
Yeah.
But this book, okay, you gotta have this every day because we're going to be going through it page by page.
Okay.
So I'm going to be having my book out here. and going through it, and we're going to be trying to read it. So this Unit 1 reading guide and questions, what I'd like you to do for Thursday is look at pages 1, oh gosh, let's try it, 1 through 9. And I just want you to read through that and start looking at some of the stuff in here on the reading guide and questions. Because I want to start working on this on Thursday especially, because we have to get the math and the chemistry first. So this first section is going to be thermodynamics. Actually, it eventually goes into thermodynamics. And there's a lot of interesting things, but what we're going to use is we're going to use this first section of the book to kind of focus on what's going on in terms of math. Okay, so there's your assignment. What we're going to start with today is pure math. So let's go to the math worksheet. And I will go in here and show in the folder. And I will allow it to open. So do you have your math worksheet there? Can you get, do you all have access to a printer? Okay, now, how many of you have Epic Pen or a writing utensil on your computer?
I do.
About to get one.
No.
I mean, you can write with a mouse, but it might be a better idea. Okay, so what we're going to do is if you take a look at this first worksheet, it says in here, plot and describe qualitatively and describe the slope qualitatively. Okay, and then we have to figure out what this is. So the very first thing that we want to kind of look at here is this concept of this. F of x is the same thing as y equals x equals x. So when I look at a graph, okay, what is this axis called?
X-axis.
X.
Okay, do not call it the x-axis. If you ever call it an x-axis, I will fail you. No, I'll fail James.
What?
Horizontal?
Well, you could say horizontal. That would be fine, and this is the vertical axis. Okay? Now, in this case, we say this is x because why? It represents this variable x. This axis becomes the variable y. So that's where you get the term x and y axis.
Indeed.
But what we're really saying is that this is the function of x. So we would label it f of x, which is the same thing as y. So what axis is this? Well, it's the f of x axis. Now, in actual terms, this is called the abscissa. This is called the ordinate. And I always think that it's a better idea to try to have a better vocabulary. I wish the math teachers never ever called it an x and y axis because it causes a lot more problems. So so you were saying how x functions. Now, if you guys took me for intro, do you remember my definition of a function?
No.
I always tell my students, do not write this down. So I don't know if, I know, Bruce, you took intro with me, right? And Jacob, what do you say? Do you remember what the definition is?
Trying to remember.
A function is something that takes a number and it funks around with it. But the thing about a function is you always know what you're going to get back. A non-function says you might have two values. So for instance, the function might be x squared. So if you give me the number 3, I plug it into this function x squared and I get back 9. If I give you the square root of x and I plug in 9, you get back 3, but you might get back -3. There's two answers. So that makes it not a function. So a function in actual better definition is for every point on the abscissa, there is only one point on the ordinate. And that's the first time in my life I've ever defined a function that way. But that should make sense. So what I'm saying is that for every point, over on this axis, in this case the x, there's only going to be one point on the f of x axis. So what would this function graph as? If I plug in x, like if x is 1, then y, or f of x, is also 1. So what does this become? This graph is a straight line. Okay, and we're assuming that the values on the abscissa and the ordinate are going to be the same values. So 1 corresponds to 1, 2 corresponds to 2. Now, sometimes we see straight lines and we think, oh, they're the same. It's a 45-degree angle. Only if the axes are labeled according at the same ratio, the same size. So if I said to you, describe this function qualitatively, what would you say? Nick, let's start with you, bud.
Qualitatively, I guess I'm thinking through like different ways of saying it, but
Well,
I guess for
try something, because right now, one of the things that I think I'm pretty good at is I'm good at trying to get people to think correctly. So what I really need from you guys is just to go ahead and try, and eventually you'll understand what I'm asking for and why I'm asking for it. So give me your best shot.
for input X, outputs the same input, I guess is one
Okay,
way.
I like that. So you're saying the value that you're putting in, remember I said a function is something that takes a number. So the numbers you put into it, by the way, what do you call the numbers you're putting into the function?
Oh,
Inputs,
Variables.
variables.
You're using input, and that's fine, but there's a name for the numbers that you plug into a function. What's that word?
footers?
Starts with the D. O.
Domain.
Domain, right? So what Nick said as the inputs is really called the domain. What are the numbers that are legally able to be put into the function? Now, in this thing, any value x, I can put in any single number. So the domain is what I'm plugging in. And then what do you get back? And what do you call the number you get back?
Range.
Range.
It's the range. So for every domain value that you choose, what are you getting back in the range?
Same number.
The same number, right? It's the same thing. So that's what makes it a line. The other thing there's one other description that I think you should do. What happens to the range as the domain gets larger? Or in other words, as x gets larger, what's f of x getting?
Getting larger at the same rate.
Okay, so they're getting larger or they get smaller, they're directly proportional, all that stuff. And that's how I would think you would describe it. That's a qualitative description. And what I have found over the course of 30 years of teaching is that students, when they take math, are so focused on trying to get the math problems done correctly, they lose sight of what this actually means. People can do good math work, but they don't know how to describe it. So who becomes really good at math are the people who are quantitatively intellectual, right? They're super smart. They don't necessarily make good teachers. They're just super smart and they can do it. And other people are like, I don't understand this. And I knew that for myself. I always struggled understanding. It took me a while until I realized I needed to explain how math worked. Then I was able to do anything in math. So what can you tell me about the slope of this qualitatively?
Straight.
Okay, it's straight.
Straight line.
The line is straight, but what can you tell me about the slope?
The rise is equivalent to the run.
Okay, the rise rise over run is the slope. So what goes up, which is really, and what do you call what's going up is the range, is the same as the domain. So you're going to get this straight line. The rise is equal to the run, at least in this example. And there's something else, though, about the slope.
Constant.
Well, it's constant. Do you understand that the slope on a straight line is the same anywhere I am on the line? So it is a constant slope. And that's how you describe that qualitatively. So let's go to f of x is equal to 2x. How will that change in my graph?
The domain matches 2 times the range.
Half the range.
Well, yeah, James, I understand what you're saying, but
Yeah.
do you agree that the range is twice the domain? Because the
Yeah.
domain is your x. That's what you plug in there.
Mhm.
So what that means is that for every value 1, I'm going to go twice as much in the range, which means what's the slope going to become?
Steeper.
It's going to be a steeper slope. Okay, so do you agree that the slope is 2, which is how we look at an equation of a line, y equals mx plus b. So in this case, the slope is 2. You're talking about still a constant slope, but the line is going to increase quicker. What kind of relationship is between the domain and the range?
It's still 1-to-1, meaning one value in, one value out.
Okay, but the thing is about a function, it's always 1-to-1. A function has to be. But there's something else about, well, what was the question that I just asked you?
Is the Earth flat?
There's still one other thing about this. What did I ask you, Jim, that you just answered? Boy, my mind's slowing down. I need to be in a classroom. I need to be standing up because this is horrible. By the way, I'm getting here on Thursday. Woo-hoo.
You were asking what I thought was the correlation between one domain value and one range value.
That's true. But I think I was saying something about the slope. Not only is it twice as much, but it's still what?
It's still a straight line.
It's still a straight line. It's constant. So if it's a straight line, then what do we say about the relationship? It's linear.
Oh, okay.
A linear relationship. Okay. So just again, a qualitative understanding is that, oh, this is a linear relationship. There's linear growth. The growth is twice as fast, but it's still linear. All right, now we go to the next section here, right? And we can draw the graph here. And then we go f of x equals 2x. And how does this look? Go ahead. Can you graph it up?
You drew it above.
No, I'm sorry. The f of x equals x squared.
X squared, okay.
Sorry.
Well, x can have two values, plus minus.
Well, no. X can still have any value.
Oh, I see what you, yes. It's
It's
parabola?
the parabola. That's not the greatest parabola in the world, but again, this is what you would draw with a pencil and pen. And if I wish I had my document camera. Maybe I should go borrow that. But anyway, this is going to be so much better if you think of it is this way. So again, x, which is your abscissa, goes on for how far?
Infinity.
Infinite. So I can plug in any value on this line, positive or negative. And then I take that value, I square it, and there's going to be exponential growth, right? We know this is an exponent, but we can go negative on x, but then what does y become? or f of x, it becomes positive.
Positive.
So the domain is all real numbers, but the range is only what numbers?
Positive.
Positive numbers, 0 or greater. All right, now describe for me the slope.
Two X.
Well, no, I mean qualitatively.
Oh,
See, and this is the problem, is we want to make sure that we're dealing with qualitative, not necessarily quantitative yet.
It's still technically constant, right? Or am I thinking
Okay.
of constant differently?
What is the slope at this point here?
it's the tangent to the curve.
Oh, so
It's going to be like this.
Yeah.
And what is the slope over here? So as this
No,
curves up,
it's
do you
not
agree the
constant.
slope is getting more?
yeah,
Mhm.
What's the slope over here?
Getting less at the same rate.
Well, don't worry about it at the same, I guess you could say getting more or less at some rate, but I'd be careful of the word rate because then you start talking about time. But do you agree that the slope is changing as I go this way, right? As I go in the positive x direction, and I should use this as an arrow. As I go this way, the slope is getting bigger. What is the slope, by the way, at this point when x is 0?
0.
0.
0.
There is no slope, right? It's the bottom of the curve. So if you put a ball in there, the ball would roll down and it would just sit in the bottom, and it has no reason to move. If it goes up, you're going to get a steeper slope. So depending on where along this curve I start like a marble, if I start it way up here, it's going to go a lot faster than if I start it down here. So we are talking about a slope that is changing, that the higher the value in the domain is, the greater the slope. So it's not a constant slope.
No.
And then the question is, well, how do I know what that slope is? I want you to go over here. What is the slope here on this first function?
1.
1.
1, right? Y equals mx plus b, the slope of a line. And the slope was that 1. That's, you know, we assume the 1 is in there. What's the slope here?
2.
2.
2, okay? The slope of a function is what we call the derivative. So when we talk about something, this is called the derivative. So I'm going to write in here.
This. Can you repeat that one more time? Sorry.
Hold on. I got to get derivative. And I need to go a little bit larger on that. Well, I didn't get to go large on that. Can you read it?
Yep.
So the slope at any point is called the derivative. Or really, the way that you would learn it in math is to say that, well, what's the derivative? It's the slope of the tangent at a point. Or basically, you're just describing the slope of these lines. So over here, the green line has a slope of 1. This one has a slope of 2. So let's just take a look at that linear idea. And now we're going to go to this. This is where I'm going to explain to you how some things work. So I'm going to start here black, and I'm going to go and the reason I say that here is that this first example, so basically what I'm saying is that this guy here is dx equals 1.
dx over dx or dy over dx?
Now dx. Okay, so what I'm saying is that the way that I write this is called the derivative. So, you guys all say it,
That's a question.
It's a question.
right? What is the question? How does f of x change with respect to x? Okay, how does it change with respect to x? Well, you, Jim, you might say, well, isn't that going to be this one? Where's, come on, why are
Ran out of ink.
I think what it is I have to learn my little buttons here. So you're thinking dy dx equals 1. But what is y? See, y is the same thing as f of
Right.
x.
Yes.
Different thing. So we're saying
Different notation.
the function change as you go in the x direction. Well, does the change is 1. For every x I go, the change is 1. So for every time I go over 1, I go up 1. That's the slope. So, but what is f of x equal to? What is the function of x? And the answer is it's x. So you'd write dx equal 1. Now that should look to you like an algebraic function where I have the same in the numerator as I have in the denominator. And so of course that's going to have a value of 1 because whatever's in the numerator is the same thing as in the denominator. Does that make sense to you? Okay. Now, James, you've not had calc yet?
No.
Does that make sense to you?
Yeah, I believe it does.
Okay. So what happens here? And I'm going to go df of x, so f of x dx. But this time I'm going to say this is derivative of 2x dx.
Okay. I see what you're doing.
Okay, so I'm using the second number here, the second thing. Well, how does the function change with respect to x? Well, what's the function? Well, the function is 2x. Now, how does that change with x? For every x, where do I go up? For every 1, I go up 2. So the answer to that is 2. Now, here's the thing that we need to kind of look at, because I'm doing this more as a qualitative understanding. I mean, I'm using numbers, but I'm explaining how things work rather than how to do, following rules. I'm saying, how does this function, 2x, change as I go in the x? Well, for every x I go, I'm going to go up 2, right? But we also said that this thing, which we call a what? What is this thing called?
Derivative.
A derivative is the what of this function?
Slope.
It's the slope. Do you agree that the derivative of this function with x, the slope was 1? Here it is with 2.
Right.
So what that gets to is I start to generalize a little bit here. Oops. Let me start to generalize that if I take the derivative of nx with respect to x, I get n.
Okay. Okay.
I get basically a constant. Now, there is something that we are going to see called the chain rule. So I'm going to jump over here for a second. And, whoops. And I'm going to go over here. Okay. This is my whiteboard, but it's going to be a little bit kind of weird. So the derivative of nx with respect to x, this is how does this change with respect to x? I can say that this is and this is, I'm sorry, I've got to learn to get my writing. This is called the chain rule.
Is that n dy dx?
No, x, this is n dx dx.
Dx. Okay.
Just making sure I'm reading that right. N dx over dx plus x dn over dx.
Correct. So do you see what I'm saying here? I'm bringing out, it's like if I took, I can't. I'm asking you, how does this change? Well, this changes by this changing with respect, this changes while I multiply it by this times this as I multiply it by this. And that's what I've got here. So this is, what is n in this case, guys?
Slope.
Constant.
Okay,
Sure.
in this case, you're saying slope, and that's
Yeah.
totally awesome. But in this case, it's a constant.
Yeah.
So dx dx, how does x change with respect to x? You've already figured this out. This becomes 1. So this is just n times 1. Do you agree? Then I say x times, how does a constant change as I go in the x direction?
It doesn't.
It doesn't. So what does this become?
0.
0.
0. And x times 0 is 0. So what does this become? Equals 1. So the derivative of a constant times a variable with respect to that variable is just the constant. So if I said to you, what's the derivative of 8x with respect to x?
8.
8.
Oh, I'm going to try this again. I've got it. I need to figure out the way that I can. Ooh.
Oh no!
Oh,
Rip the calculus.
There we go.
Thank God for undo buttons.
That's right, damn it.
Mhm.
So let me just erase this and go back to my pen. So I'm over here. If I go d8x dx equals what?
8.
It's equal to 8, right? So that's pretty straightforward. Hey, what if I said, what's the derivative of 8 with respect to x?
0.
Right? How does 8 change as I change x? Who cares?
doesn't.
8 is constant. So there's it. So the answer is exactly what he said. It doesn't. There's no change. So the derivative of a constant is always 0. But that should make sense, because what does a constant graph as? It graphs like this. Here's my graph. Gosh, these are ugly, ugly diagrams. Here's my graph. Here's equals the constant. How does this change? What's the slope of this? There is no slope. It's 0. That's what that means. Okay, now let's do this. I'm going to go rewind a few of these things. Start to fix my chalkboard a little bit. Oops. Let's try this one. Now, if you've had calc and you know this, don't scream out the answer.
Deja vu.
I mic off and scream it, I guess.
Now, James, you've never had calc, so how would you do this?
How does x squared change in relation to x? Well, for every x you have x squared, so it would be some sort of exponential change, wouldn't it?
Not necessarily, but you look at the chain rule. Do you agree that dx squared, dx is actually just d times x times x
Yes.
dx? What's the chain rule say?
Well, you would set it up as x dx over dx plus x dx over dx.
Good. Nice job, buddy. What does this become? 1, 1. X plus x is what?
2x.
2x.
Ta-da!
What do you think of that?
Yay!
All right, let's go crazy. Using the chain rule, now I know those of you who've had calculus, this is a really easy derivative, but using the chain rule, can you explain to me what it is?
Same thing as the previous one, but an additional plus x over dx over dx.
Well, this is, do you agree that this is dx times x squared all over dx,
Yes.
which is equal to x times the derivative of x squared dx plus x squared times the derivative of x dx.
Well, I gotta move my zoom bar. There we go.
Okay, does that make sense to you? But I already know that the derivative of x squared with respect to x is 2x plus x squared times 1. So I get 2x squared plus x squared, which equals 3x squared. What do you think, boys and girls? Sorry, no girls.
Ah,
You're gonna give them this, I guess the simple way to notate it.
I'm going to show you a simpler way to know how to do these things. But does that, using the chain rule, make sense?
Yeah, so if I'm getting it right, you pretty much break it down, just break down the formula into its most base parts and then
Yeah.
together.
But you want to know something really easy? This is even easier way to know this, and this will always be okay. I take this number and I put this number in front, 3, and then I drop this power by 1. That's it. It's called the power rule. So 3. So do you agree that's what it came out to be? So if I said, what's dx to the 5th with respect to x? Bring the number in front. What do you think?
I'm going to be writing that down.
I mean, does that make a lot of sense? I hope it does.
I guess a good way that I remember it too, just kind of if you plug in the numbers too, if instead you put the 5, you just put n.
Oh, yeah. So
Yeah.
if I want to generalize it, I go
Yeah.
derivative of x
To the end.
Of
to the n dx is equal to n x to the n minus 1.
Yep.
And there you have it. That's called the power rule. Now, I want to go to something completely different here. So I'm going to go ahead and get rid of all this. And I'm going to say try this one. Dx to the fourth dx equals 4x cubed. So over here, I snap, what do you say?
That's a
That's a
question.
question.
That's the question. How does x to the fourth change with respect to x? So as you go x, how does x to the fourth change? Well, it's going to change times 4 times whatever that value of x is to the third power. I mean, it's a little bit more complicated, harder to qualitatively see it in your mind, but that's what it is. But you understand this. How does this function, x to the fourth, change with respect to x? Now, this is not totally legitimate, but it's kind of acceptable. Watch this. You see I only multiplied through by dx? So at this point I say, well, how does this function change? Not with respect to anything. I just said, how does this change? And the answer is, it changes for x to the third times how x changes, times the change in x. And so this just becomes a different way of looking at this feature and saying, I don't have to have it over with respect to something. I'm just saying that function changes this way times whatever the change in x is. So if x changed by 1, then whatever, so in other words, if x equals 8, now let's undo that. Let's go x equals 2. And I say dx equals 1. So let's take a look at this. What is 2 to the fourth?
16.
Okay, 2 to the fourth is 16. And then what is 3 to the fourth?
Mm,
3, 9, 27, 72.
No, try again. 9
Um,
squared.
81. Yeah.
Okay.
Duh.
So what's x to the third? What's 2 to the, but do you understand? I don't know what x is. I know
X to the
dx
third.
is 1. What is x to the third? If it were 2, it would be 8 times 4 would be 32.
Mm-hmm.
If x was 4, if x was 3, this would be 27 times 4. What's 27 times 4?
$112.
Okay? So I don't know which one it is, because do you understand that I'm looking at a graph that may look super exponential, and I'm going from there to figure out what the value of x has done. X is not constant. X keeps changing. So when I have dx being really big, I don't know what value of x to put in here. Right? I know x has changed by 1, but what's the value of x? It's either 2 or it's 3, which gives me the answer of either 32 or 112. Neither one of those is even close to being the same. So what I can do is, what if I go closer and closer together? What if instead of 2 and 3, I went 2 to the fourth and 2.1 to the fourth? Then I'm going to get an answer that's a lot closer together, still different. What I will eventually want to do is have 2 points that are infinitely close together. So what does dx equal?
1.
No, if they're the same,
Oh, 0.
that doesn't make sense if this is 0. So what we tend to do is we don't say 0, we just say dx, whatever that changes. And it's an d, the derivative, is infinitely small. So in life, in general, if I'm looking at a finite change, I have delta x. If this becomes close to 0, then this becomes dx. So how big, let's see if I can show you this. Let me, over here, this is a delta x. There's a finite distance. If I bring that distance, how much distance is there between points now? It's getting smaller and smaller and smaller. How close can I get? It goes really close to 0. And so what instead of calling it 0, I'm going to call it dx.
So what you wrote there is basically a limit.
It's what we call limits. Yeah, and in calculus, you spend a lot of time dealing with limits and limits and limits and limits and limits. But I think if you can understand that this area, this distance between my fingers is delta x, eventually it gets smaller and smaller and smaller until they're infinitely small, then that distance is now called dx. dx is an infinitely small distance. To show you some idea of infinitely small, let's try something like this. I'm going to take a graph. Okay, there's my axis. And I'm going to take the graph and I'll use, oh, I don't care, we could use red. Okay. Now, in very simple terms, I'm going to show you something kind of cool. I'm going to go over here and say that this point is 0. This point is 0, and this point is 1. And this is graphing f of x equals x. Does that make sense to you guys?
Yeah.
Okay. Calculate the area underneath that curve. And not with any calculus, this is just algebraic. What's the area underneath that curve?
There's a formula for a triangle, area of a triangle.
1/2.
Yeah. 1/2 base times height.
Yeah.
And again, you know, you could look at this a couple of ways. You could say, well, what if this were a rectangle like that? Do you agree this would be 1 times 1, because this is f of x equals x, so 1 times 1, but I'm only looking at half of it, so it's 1/2. Do you agree that the area is 1/2?
Yes.
Okay. Now, let's go crazy here and try this. There's one rectangle. There's another rectangle. Okay? Do you think that these two rectangles approximate the area underneath the curve?
Say that again.
These two rectangles, if I added them together, would be twice the size of the area underneath the curve.
Yes.
Mm-hmm.
So let's try this. Instead of doing those rectangles,
Oh, I see what you're
let's
saying.
try a rectangle like this.
Yes.
Right? So in other words, the area underneath that curve is this area, right?
Right.
Plus this area, but not this area.
Right.
But I didn't count this area. But do you agree that this area and this area are the same?
Yes.
Mhm.
So it kind of does. So how do I do what is the size of these rectangles?
Half.
Half by half.
1/2 by 1/2, right?
Yeah.
It's a quarter. But how many rectangles do I have?
2.
Two. Fair enough. Okay. Let's forget about that. Let's do this. What if I said I'm going to draw a rectangle here, 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 and here.
Hmm.
How many rectangles do I have?
5.
5.
I got 5. Am I going to overestimate the area or underestimate?
Over.
Over.
Over, because I keep going on here getting all this stuff too much. So let's change the way I think about drawing rectangles and instead draw a rectangle like this. This is probably a little bit too big. Oh, that's crappy. Hold on, let me make them a little bit thinner.
Are those rectangles getting infinitely smaller?
Well,
Are they?
I'm hoping that you kind of understand what I'm trying to do. If I have half the rectangle not measuring, so I'm missing, like over here, if you can think about this, I'm not measuring this area. I'm not measuring this area, but I'm measuring that area, and they kind of cancel each other out. And I'd be not measuring that area, but not measuring this area. Does that make sense?
Mm-hmm.
So what I'm saying is that in this scenario, I am looking at the value of x right there at the middle point. So I kind of take the middle point and then multiply the rectangle. Do you agree that the area that I'm counting and not counting becomes smaller and smaller, those little triangles, as the rectangles become narrower and narrower?
Yes.
So what if I did infinitely small rectangles? Infinitely narrow rectangles.
Then you get that area that we calculated earlier.
D of
Okay.
X.
So let me ask, oops, where's my pen? Oh.
Eventually.
So let's say that I make these rectangles infinitely small this way. How big are they?
0.
No.
DX.
Or DX.
Yeah, right? They're dx small. It approaches 0. We
Yeah,
can see
okay.
0. So, but what's the top of the rectangle going to be? Where's the center point going to be if you have an infinitely narrow rectangle?
F of X.
Won't it be f of x? So what's the area of each of these rectangles?
F of X times D
DX.
of X.
Which in this case is x dx. That's the area of each rectangle. How many rectangles do I have?
Infinite.
Infinite.
I have an infinite number of them, and I need to do what to all the areas to know the area underneath that curve?
Sum them up.
I need to add them all together. Well, that adding them all together is called, it's this symbol. It's like a big S. And that stands for,
Integral.
let me get What the heck is this? That is integral. And this is where we get the term integration. It helps if I spell right. Integration. Okay? So we are integrating. And what does integration mean? Integration is the summing up of an infinite amount of triangles, of rectangles that are infinitely narrow. So you might want to write that down. Integration is the summing up of an infinite number of rectangles that are infinitely narrow, and they're tall. And how tall are they?
F of X.
How is the slope?
F of X. They're F of X tall, right? They're whatever that function is, F of X tall. Now we know that the answer in this question, is 1/2. We know that. So somehow I have to figure out, well, what the hell does this mean? And how did I get there? Now, here's what I want you to know. How long is this red line? I mean, how far does it go from left to right?
Plus minus infinity.
No, just the red line is not infinitely long.
Oh, it goes from 0 to 1.
1.
It goes from 0 to 1. So what I'm saying is I'm going to sum this up. Am I going to infinitely sum it up forever, all the way
No.
to the right and all the way? I'm going to sum it up
Between
from
0 and the interval 0 to 1.
equals 0 to x equals 1. Now that's called the limit of integration. That's where I'm adding up those rectangles. Okay, now here's the thing about notation like this. Sometimes you will see it from x equals 0 to x equals 1, and that is totally legitimate. But a lot of times you will see this. Let me get rid of this, and you'll see it like this. This is how you'll see it. The summation, the integral from 0 to 1 of x dx. Now, 0 and 1, you're saying x equals 0 or x equals 1. You're saying on the domain, on the abscissa, where exactly are we going from where? So I'm looking at the integration of this. So what is the integration of any function? The answer is the area underneath the graph. Okay, I'm going to show you something here. And I'm going to go to here. And this is something that's driven me crazy. If I say flatten the curve. I just want to show you something. This is what's amazingly stupid. Do you agree that this is without social distancing, whatever you want to say, right? This is an area underneath the curve.
Right.
This is area underneath this curve.
Right.
What's the difference between these two? The answer is the area is the same.
Be the same.
This one just has a bigger area in a smaller domain. This is what I've never understood. The amount of people who die from COVID should be the same no matter what.
Lies, damn lies, and statistics.
You don't want this because this is your healthcare system capacity. You don't want the height to go, but the area is the number of people who die. Now that's one way of looking at this. The other thing is if I look at Planck's black body radiation. Do you guys remember what that is? Have you taken this?
Mm-hmm.
Okay.
I definitely don't think I've seen this one.
Okay, this is an intro. So if you've not taken intro, you'll see a graph that looks like this. So let me just show you this graph here. This is the wavelength, and this is how much radiation an object is giving off. Okay, how much radiation an object gives off, and this is a commercial. The area underneath the curve represents how much total area is coming out of an object. So this curve, if you guys recall, some of you will know this, if not, this curve goes on forever to the right and forever to the left because it's a logarithmic scale. So I have to integrate it from where to where?
Plus minus infinity.
Negative infinity to positive infinity. And yet, there's still going to be an area underneath the curve. And we do that by creating small rectangles that says, well, it's the function and it's dx. That's all it's doing. Now, do you know what this function is? And the answer is no, you don't.
Planck's law, isn't it?
So let's go to and of course we can go in here. I'm going to go ahead and hide this. There's the function.
Ah,
Right? That's a scary function. But look what's going on over here with this function. Do you see the function which is related to two things, temperature and the frequency? But, so I'm not even worried that much about you understanding everything. But what am I doing it? I'm integrating this function from one wavelength to another wavelength, and that's the domain. That's the abscissa. And what is the abscissa? It's wavelength. So I'm integrating this function times the infinitely small change in the wavelength. And that gets me a total amount of radiation. So you look at an equation like this, and you probably are sitting there to yourself going, oh my God, I am freaked out. This is so much math. But I want you to see what you have to see. In this equation, this is some function. This is an infinitely narrow rectangle along the abscissa. This is how far am I going? I'm going from one wavelength to another wavelength. That's how far I go. It's what we call the limits of integration. And that's all it is. Now, the funny thing is, this function in the middle is the hard part, because I don't know what those functions are. And obviously, there is an equation over here that looks really nasty. And this is actually multivariable because I've got nu, which is frequency, and I have temperature, which is something else. Okay, so it gets a little bit hairy in the functions. All right, now, so where exactly are we in all of this? Well, let's get out of here. We don't need this. We go back to our blank screen. No, we go back to our math worksheet. No. Math worksheet. And we go, oh, here's some functions. Here's x, here's 2x, here's x squared. And then the question is, how do we get this information here? And this becomes working backwards. So I want you to see this. This is where it gets a little bit hairy. So this is a little bit freaky. This should freak you out just a little bit. You see that function, x dx?
Hmm.
That is the derivative of what function?
X squared,
Over 2.
or over 2, right?
Now, Nick, Jim, you know this because you got calculus behind you. Mike, how much calc have you had in your life?
It's been years.
Okay. Jacob, where are you in the calc sequence?
It's been a while, so
Okay. And then James? So
Yeah, sorry.
can you kind of see it working backwards?
I can definitely see the dots there.
Okay. So here, what's the derivative of x squared?
2x.
2x
2x
times dx.
times dx, right? 2x dx. That's what we said, right? What do we have here?
X dx.
So I need to have 2x dx, but instead I have x dx. So I'm missing a 2 here. So what I can think about is I can put in here, let's put it in a different color, let's go green. You know, it's so funny, I put my pen down. If I put in a 2 here, I would have to put in a 2 over there. Do you agree that 1/2 times 2, they cancel out?
Right.
So if it was 2x dx, the answer would be
X
x squared.
squared.
But it's going to be x squared times 1/2. So the integration of x dx is going to be x squared over 2. So I want you to think of this going backwards. Take the derivative of this. There's something, I'm taking the derivative of x squared over 2 dx. But anytime I have a constant, I can take that out in front. Derivative of x squared dx, and we said that's 1/2 times 2x dx. The dx's go away this time. I don't need that. But I have x dx because the 2's cancel out. Okay? Where am I doing this from, though?
0 to 1.
0 to 1. So what I do is I go over here and I evaluate this. It's a straight line from 0 to 1. This is just, you know, and the funny thing is when I taught this course, I once tried to figure out, well, what the hell is this? What do we call this thing? I don't even know what this is. This is like
An interval.
an interval. It's just a thing. It's just, there's no name for
It's a
that line.
notation.
It's just a line. And this line says 0 to 1. So what I do in this is I plug in 1 first. So 1 squared over 2. And then I subtract it. It's the difference between there and there of 0 squared over 2. Which is, what's 1 squared? Last time I checked was 1 divided by 2. What's 0 squared? Last time I checked, 0. So it's 1/2. That's the answer. And that's the area under the curve, and that's what we have. Now, what we have here are a whole bunch of other functions. And these are the functions, these are the basic functions that we're going to need to learn the derivative and the integral of. So what I want you to do for this Thursday is read those pages, and I want you to finish just the qualitative aspect of this. And we'll look at things a little bit later. But let's do this. Class notes. And we're going to watch a video together. I'm going to skip through it.
Yeah.
Differential calculus is a powerful mathematical tool for analyzing how things change. The handles on this tool are a few simple rules for calculating derivatives.
Somewhere around 600 BC, someone discovered that if you want to make pleasant sounding chords on a stringed instrument, then the lengths of the strings ought to be in the ratio of simple numbers like 1 to 2 or 2 to 3 and so on. These are called the Pythagorean harmonies.
By the way, this guy's like my hero. He was awesome.
The discovery was very important because it was the very first discovery of a connection between mathematics and the physical world. Unfortunately, that connection was forgotten and had to be rediscovered slowly and painfully thousands of years later. One person who certainly grasped it, though, was Galileo Galilei. In any case, I want to read to you something that Galileo wrote. This book was published in Rome in 1623, and it's called Il Saggiatore, which is usually translated to mean the assayer, but I prefer to call it the experimentalist, because I think that's more like what Galileo had in mind. Galileo had this nasty habit of making his famous remarks in Italian, but I'll translate it for you as I go along. He said, "True knowledge is written in this enormous book, which is continuously open before our eyes. I speak of the universe. But one can't understand it unless first one learns to understand the language and recognize the characters in which it's written. It's written in the language of mathematics."
He's translating as he's reading. Great. I love that.
So, to prepare to read the book of the universe, we must first learn the symbols and the vocabulary of the language of mathematics. It's a language of precision, and poetry, and even of music.
For a long time, physicists have used the language of mathematics. And since somewhere around 600 BC, so have musicians. As with just about all languages, including music, mathematics has its own vocabulary, its own rules and symbols, its precision and elegance, its poetry, and its history. One part of that history was Galileo Galilei, who was something of a nonconformist. It was a trait he inherited from his father Vincenzo, who was an accomplished musician.
Okay, so here we are, and they're going to give you this little bit of a discussion in there. And I'd like you to watch this a little bit, but when we get to someplace like this, about 11 minutes, let's go here and talk through it a little bit.
To determine the slope at a particular point, here for example, simply take another point on the hill. It doesn't matter where. Now connect the 2 points with a straight line. That line is called a chord, and its slope depends on the location of the second point. If the first and second points are reasonably close, the chord is a reasonably good approximation of the bike's path. Now, move the second point closer to the first. Move it even closer. The slope is a number, and as the points get closer together, the number gets closer to a certain value. It's reasonable to call that number the slope of the hill at that point. The line with that slope through the point is called the tangent line. And the tangent line is just what the chord turns into as the points get closer together. And the slope of the tangent line at that point is the slope of the hill. Instantaneous speed can be calculated along the same lines. Galileo's law of falling bodies applied.
Value of the average speed is the instantaneous speed. Change in elevation is divided by change in horizontal distance. The result is the slope of a chord joining 2 points when the horizontal distance shrinks to 0.
Now, do you agree that in this case, I've got this getting smaller and smaller and smaller, so how wide is this triangle?
Smaller and smaller?
Until it reaches what?
D of x.
Right? Not d of x, dx.
Dx, sorry.
Right? It gets smaller and smaller until it gets to dx, which is infinitely smaller, 0. But it's not, we don't say it's 0, it's infinitely small. Now, what would the change in elevation be? Do you agree this is also getting smaller and smaller and smaller?
Right.
But where will these 2 points lie
Between
on that graph at the same point, right? And that becomes f of x. So that's how you're determining the slope. What does this line become when those 2 points are 0? So it's the slope of the tangent. And I think in a bunch of my classes, I've talked about this, where I said the slope between any 2 points on a straight line is the slope of the line itself. Because if it's a straight line, does that slope ever change?
No.
Right? It's always the same slope, which we set on the first 2 functions. If it's a curved line, then that yellow line, as it's shown here, changes. As the points get closer together, there's less and less change. So it's the slope. The slope at any point on a curved line is the slope of the tangent. And the tangent is the derivative of the function.
The limiting value of the slope of the chord is the slope at that point.
Differentiation. The goals and calculations differ, but not the essential concept nor the process. 0. That ratio becomes a derivative, and the deltas become a new symbol.
Now it says dy dx. What have we said that y could be called?
f of x.
The f of x dx.
dy over dx, the symbol of the derivative, which means the derivative with respect to x of the quantity y. Once the simple mechanics are mastered, finding the derivative for just about anything, no harder than flipping a switch.
The derivative of a function is the slope of its tangent at each point. The derivative of a function is itself a function.
Okay, so let me go back to stop sharing. So I think in the future, I'm going to try to take at least a 5-minute break before the hour, at the top of the hour, and we're supposed to go till 10:45, but we didn't take a break today, so we'll let you go. So what I want you to do is I want you to do 3 things. Watch that whole video. It's a half an hour. And it's kind of fun. And I like, there's historical background. I think it just makes it more interesting. I want you to try to do that qualitative mathematics of those functions, okay? And just describe them in the slope. And then if you have your book right now, go ahead and take a look at something in the book. And you will see, like on page 4 of your book, you will find derivatives. And just remember the derivative, that's a question. How does x change with respect to time? See if you can understand that a little bit. The stuff on page 5 is really tough, and you will not understand that, which is okay.
Partials.
read through it a little bit, and then if you look on page 7, look at equation 1.5. And 1.5 says that the pressure at some height, at the surface in this case, is nothing more than integrating from 0 to infinitely high dz. So it's with respect to height. Do you agree that's height? What's rho?
Pressure.
No, rho.
Density.
Density. What's g?
Gravity.
So I take density times gravity and I integrate it with respect to height. And if I sum all that up, I get the actual pressure. So you're going to read through this. Now, what level of understanding do I think you're going to get by reading?
Some baseline level.
Yeah, maybe some of it you'll get, some of it you won't, some of it will be like, I don't really understand that, which is fine. That's what we're going to be teaching, is how to get to 100% understanding. You won't get it right now, I don't think. There's a lot of little things in there that take some time. And then so your video, your math sheet, and just reading through that and trying to understand it. And on Thursday, this is where we'll pick up. You feel okay with the stuff we did today?
I think so. Definitely would like more practice in the future, just to be sure.
Well, we're going to get tons of practice, so don't worry about that.
Good.
Okay, so I'm going to put that up on the climate thing. I'll send an announcement as to where that is if you didn't get it, but that's the recording.